today our topic is application of Opamp. Previous class we discussed about what is the Opamp characteristic, its functions, and today we have discussed about the what are the application of Opamp. So first of all, Opamp acts as a inverting amplifier. How it is acts as a inverting amplifier? So if we see the configuration of Opamp, this is the non-inverting inverting terminal, and here we applied R1. From the figure, we use that op-amp circuit as a single resistor R1 and feedback resistance RF is used, and the V0 we take the output and input is V1. Suppose we are applying a sinusoidal voltage here, so what we get inverting means 180-degree phase shift at the output. So the if we see that from the non-inverting terminal it is grounded, so the voltage at this point, suppose this is point P, is 0, so point at this point the voltage will be 0. This is if it is the virtual ground. So if we see that at point P we take the I1, we get V1 minus 0 by R1 current, and I2, suppose this is the I2 current, I2 equal to 0 minus V0 by RF. So using Kirchhoff's current law KCL for point P we applied, then we see that I1 equal to I2, current entering is equal to current leaving. So I1 is V1 by R1, it's nothing but minus V0 by RF. So V0 by V1 we get minus RF by R1. So the RF by R V0 by V in V1 the means gain. So gain, voltage gain is equal to feedback resistance by the internal resistance. So this is we get from the inverting terminal. If we see for non-inverting terminal, means here voltage is connected to the non-inverting V in, here there is R1 applied sinusoidal voltage, here take the feedback resistance RF, we get the same phase cycle, means the non-inverting. So similarly we take I1 equal to 0 minus the voltage at this point V in P, because this is V in, so I in equal to 0 minus V in by R1, and I2 equal to V in minus V0 by RF. So similarly using KCL at point P, what we get, current entering is equal to current leaving, I1 equal to I2. So what we get, V minus V in by RF equal to sorry, 0 minus v in by Rf means minus v in by Rf equal to v in minus v0 by Rf. So if we calculate, then we get v in by Rf equal to v0 by Rf minus v in by Rf. So if we take v in 1 by Rf plus 1 by R1 equal to v0 by Rf. So v0 by v in we get 1 plus vgrf by R1. Next, if we see the adder circuit, what do we see? Adder or summer? Addition. This is R1, R2, R3. Non-inverting terminal is grounded. We applied R0, R, I. Suppose I1 current, this is the I2 current, this is the I3 current. So current entering is equal to current leaving, I1 plus I2 plus I3 equal to I at point P. Similarly, if we use KCL, so I1 we get P1, here it is 0 means the voltage at this point 0, so V1 minus 0 by R1 plus V2 minus 0 by R2 plus V3 minus 0 by R3 equal to 0 minus V0 by Rf. So P1 we get minus V0 by Rf, and if we take R1 equal to R2 equal to R3 equal to Rf equal to R, then V1 plus V2 plus V3 equal to minus V0, or V0 we can write minus V1 plus V2 plus V3. So adder or summer, we see the voltage are add here. Then if we see the subtractor circuit, what is the for subtractor? For subtractor, here we applied negative, here we applied for the non-inverting terminal, here we give R1 resistance, suppose this is V1, here V2, from output we take the V0 voltage. Similarly, suppose this is point P, here the common voltage is V3. So again, since the voltage input terminal of the op-amp is 0, so no A and B are same potential, and we take it is V3. If we applied for the first V1 minus V3 by R1 equal plus V0 minus V3 by R2 equal to 0, first equation for this loop. For the second loop, we take V2 minus V3 by R2, sorry, R1, this is the R1 resistance, plus V0 V3 0 minus 0 minus V3 or by R2 equal to 0, equation 2. So we simplified the equation. Here we get, what we will get, the from the first equation we v3 v2 by r1, we get v3 1 by r1 plus 1 by r2 from the equation. So if we replace v3, so from the first equation, so we get v3 v2 by r1 equal to v3 from the first equation, v1 by r1 plus v0 by r2 equal to v3 1 by r1 plus 1 by r2. So from the equation we can write this is the v2 by r1, so v0 by r2 equal to 1 by r1 v2 minus v1, so v0 equal to v2 minus r2 by r1 v0 by v2. So this is the output voltage is difference between the two input voltage we get. Next, if we see the what is for differentiator and integrator circuit. Differentiator and integrator, if we see, then there will be a difference. We use the a capacitor is used as a feedback resistance. Means then this is the non-inverting terminal grounded. Here we use capacitor. Here there is a resistance output P in. Suppose this is point P. So suppose I is the current I2, this is the IU. So I equal to, we know that dq by dt. So q equal to cv0. cv0 means ever here v equal to v in. So I we take d by dt, c v in means c dv in by dt. Here current entering I1 same equal to I2, so c dv in by dt is equal to, we write v0, v0 means 0 minus v0, current is I2 is 0 minus v0 by r, or v0 we can write minus ir. So c dv in dt we can write minus cr dv in by, if we put the value c dv in dt here, we get v0 equal to minus c dv in by dt. So output voltage v0 is equal to derivative of the input signal with a constant rc. Then if we take integrator, what we see in integrator, opposite the previous one, here there is a capacitor, this is the output voltage c I. So here I equal to I in equal to v in minus 0 by r, means v in by r. This is similar to here the current is output is 0, previous case same as c dv0 by dt. So if we take dv0 by dt equal to 1 by rc v in, so v0 equal to minus 1 by rc v in dt. So output voltage is integrated to the input voltage. So these are the application of Opamp, means it's as the addition, subtraction, differentiation, integration. Here are the various application.